I want to describe a specific and unusual situation in theoretical physics. We have two extraordinarily successful theories. Each has been confirmed with extraordinary precision against thousands of experimental measurements spanning a century of physics research. Each describes a domain of nature that the other cannot reach, and between them, in the space where both should apply simultaneously, something has gone deeply wrong. The two theories are quantum mechanics and general relativity. And the space where both should apply is the Planck scale. Distances of 10 to the minus 35 meters, energies of 10 to the 19 GeV, densities of 5 times 10 to the 96 kilograms per cubic meter. At this scale, both quantum effects and gravitational effects are simultaneously important. And at this scale, physics, as we currently understand it, breaks down completely. This breakdown is not a minor technical issue. It is not an imprecision at the edge of a theory's range of validity, the kind of approximation error that a better calculation could fix. It is a fundamental conceptual failure. The two theories that describe essentially everything we have ever observed give mathematically inconsistent answers at the Planck scale. They cannot both be right. They must both be incomplete. And the theory that replaces them both, the theory that correctly describes the Planck scale, is the final secret of the universe. I want to be precise about why I use the word secret. The universe does not hide things deliberately. There is no agency behind the fact that quantum gravity is inaccessible to current experiments. But the physics of the Planck scale is hidden from us in a specific and systematic way. It is hidden at the scale where quantum and gravitational effects simultaneously matter, which is a scale 14 orders of magnitude smaller than anything a current particle accelerator can probe. To call it a secret is to acknowledge that the universe has a structure that our best theories cannot yet reach, and that reaching it will require the most fundamental conceptual transformation in the history of physics. Let me give you a sense of what 14 orders of magnitude means in physical terms, because the abstraction of the number can obscure how genuinely hidden the Planck scale is. The Large Hadron Collider at CERN probes energy scales up to approximately 14 TeV, or 14,000 GeV, in proton-proton collisions. The most energetic cosmic ray particles ever detected have energies up to approximately 3 times 10 to the 20th electron volts, or 3 times 10 to the 11 GeV. The Planck energy is approximately 10 to the 19th GeV. Even the most energetic cosmic rays ever detected fall short of the Planck energy by a factor of approximately 30 million. No natural process known in the observable universe produces particles at the Planck energy. No accelerator we could build within the observable universe, even using the entire mass energy of a star as its power source, could reach the Planck energy. The Planck length is even further from our experimental reach. The LHC probes spatial scales down to approximately 10 to the minus 19 meters, the scale of a quark. The Planck length is 10 to the minus 35 meters. The difference is 16 orders of magnitude. The ratio of the size of the LHC's minimum resolvable scale to the Planck length is 100 million billion. We are as far from the Planck scale in our most precise experiments as the Planck scale is from the size of a proton, and the proton to the Planck scale ratio is itself 1,000 trillion to 1. This is the depth of the secret, not a riddle that a cleverer experiment or a faster computer could solve, a gulf so vast that bridging it requires not just better technology, but a fundamentally new conceptual framework that allows us to infer the Planck scale physics from measurements made at scales that are orders of magnitude larger. This is possible. In the same way that chemists of the 19th century inferred the existence of atoms from the large-scale properties of gases and crystals without being able to see a single atom, but it requires the kind of theoretical insight that has historically arrived not incrementally but in sudden revolutionary steps. Let me build the argument for why this secret must exist, why it cannot be avoided, and what the various approaches to resolving it suggest about the nature of space-time, matter, and existence. The incompatibility of quantum mechanics and general relativity is not a new observation. Physicists have been aware of it since the 1930s, when the first attempts to quantize the gravitational field were made. The specific nature of the incompatibility has been clarified over decades of work, and it is more fundamental than a mere technical difficulty. There are two independent aspects to the incompatibility, and both must be resolved by the final theory. The first aspect is the fixed background problem. Quantum mechanics is built on the concept of a fixed classical background spacetime. The Schrödinger equation uses time as a fixed external parameter. The position operator is defined on a fixed spatial background. The framework of quantum field theory, which combines quantum mechanics with special relativity, is formulated on the fixed Minkowski spacetime background. This background is fixed in the sense that it does not participate in the quantum dynamics. It is the stage on which the quantum drama plays out, not an actor in it. General relativity requires a dynamical spacetime. The metric tensor, the fundamental dynamical variable of general relativity, evolves according to the Einstein field equations. The metric is not fixed. Different solutions to the Einstein equations describe entirely different spacetime geometries. When you try to define quantum mechanics on a background whose geometry is determined by the quantum state of the matter it contains, you face an immediate circularity. The quantum state of matter determines the geometry, but the geometry determines the quantum dynamics that gives you the quantum state. The second aspect is the non-renormalizability problem, which I will describe in detail in a moment. The two aspects are related but distinct. The fixed background problem is a conceptual issue that arises even before you attempt any calculation. The non-renormalizability problem arises when you actually try to compute quantum corrections to gravitational processes. Let me describe both in sufficient detail to understand why they represent fundamental rather than technical barriers. The fixed background problem becomes most acute when you consider a quantum superposition of macroscopic configurations. In ordinary quantum mechanics, a massive object can in principle be in a superposition of two distinct locations. This is not just a theoretical curiosity. Quantum superpositions of massive objects have been demonstrated experimentally, with the current record for quantum superposition of the largest objects involving molecules containing thousands of atoms. The principle extends in quantum mechanics to arbitrarily large objects. If a massive object is in a quantum superposition of two locations, what is the gravitational field of this superposition? The gravitational field is determined, according to general relativity, by the distribution of matter and energy, which in this case is in a superposition. A gravitational field in a superposition of two configurations is a quantum superposition of two space-time geometries. Such a quantum superposition of geometries is not described by classical general relativity. It requires a quantum theory of gravity. Several experimental groups have proposed or are actively working toward experiments that could directly detect the quantum nature of gravity by observing quantum correlations, specifically entanglement between two masses that interact only gravitationally. If gravity can entangle two masses, then gravity must be capable of quantum superposition, which would directly confirm that the gravitational field must be quantized. These experiments, involving masses of approximately 10 to the minus 14 kilograms held in superposition for periods of seconds, are at the frontier of experimental physics and have not yet been conclusively performed, but they represent a direct experimental test of the quantum nature of gravity that does not require accessing the Planck scale directly. The non-renormalizability problem is more technical but equally fundamental. When you write down the Einstein-Hilbert action for gravity and attempt to treat the graviton, the hypothetical quantum of the gravitational field, as a small perturbation around flat spacetime, you can write down Feynman rules and compute quantum corrections to gravitational scattering processes order by order in the gravitational coupling constant, which is Newton's constant g. This is the perturbative approach to quantum gravity. At first order, the calculations give finite results. The graviton scattering amplitudes can be computed and agree with the predictions of general relativity in the appropriate classical limit. But at second order and beyond, loop integrals arise that diverge. In quantum electrodynamics, the analogous divergences can be absorbed by redefining the electron mass and charge, a procedure called renormalization that makes the theory predictive with a finite number of measured parameters. The theory is renormalizable. In perturbative quantum gravity, the divergences at each new order of the loop expansion require the introduction of a new independent counterterm with a new independent coupling constant that must be fixed by experiment. At 2 loops, 2 new couplings are required. At 3 loops, more new couplings are required. The number of independent parameters grows without bound as you go to higher loop orders. The theory is not renormalizable. It does not make predictions with any finite number of parameters. To have a predictive theory of quantum gravity, you need a fundamentally different approach than the perturbative expansion around flat spacetime. This is not a failure of general relativity or quantum mechanics individually. It is a failure of the procedure of combining them in the most naive way. The correct procedure, whatever it is, must produce a theory that reduces to both general relativity and quantum mechanics in their respective domains while being free of the infinities that the naive combination produces. The Planck scale is where the naive combination breaks down most severely. Below the Planck scale, the loop corrections become of order 1, and the perturbative expansion is completely unreliable. The physics at and below the Planck scale requires a non-perturbative, background-independent formulation of quantum gravity that does not exist in a completed form in any current theoretical framework. What that new thing might be is the subject of the most intense theoretical physics research program in the history of science. The 2 most developed approaches are string theory and loop quantum gravity, which I described in the space-time video. But the spectrum of proposals extends well beyond these 2 frameworks, and each proposal reveals a different aspect of what the final theory might look like. Let me describe in more detail what we expect the Planck scale to be like, because the specific physical predictions for what happens at 10 to the minus 35 meters and 10 to the minus 43 seconds are crucial for understanding what the final theory must explain. The Planck length is the unique length that can be constructed from the 3 fundamental constants that appear in quantum gravity: the speed of light c, Planck's constant h bar, and Newton's gravitational constant g. The Planck length is the square root of h bar times g divided by c cubed, approximately 10 to the minus 35 meters. The Planck time is the Planck length divided by c, approximately 10 to the minus 43 seconds. The Planck energy is h bar times c divided by the Planck length, approximately 10 to the 19th GeV. These scales are so extreme that they are difficult to give physical intuition for. The Planck length is approximately 10 to the 20 power times smaller than the diameter of a proton. The Planck energy is approximately 10 to the 16 times larger than the energy at which the LHC currently operates. The Planck temperature, the temperature of a black body radiating at the Planck energy, is approximately 10 to the 32 Kelvin. The hottest temperature ever achieved in a terrestrial laboratory in heavy ion collisions at RHIC and the LHC is approximately 5 times 10 to the 12 Kelvin, 20 orders of magnitude below the Planck temperature. At the Planck scale, the quantum fluctuations of the space-time metric are of order 1. The geometry of space-time fluctuates by amounts comparable to the geometry itself. In this regime, the smooth space-time of general relativity is no longer a good description. Space-time is expected to become something fundamentally different. A quantum object whose geometry is uncertain and fluctuating, described by a quantum state rather than a classical metric. What space-time looks like at the Planck scale is unknown. The different approaches to quantum gravity make different predictions. In loop quantum gravity, space-time is discrete at the Planck scale. Area and volume come in discrete quanta, the smallest of which are approximately the Planck area and volume. In string theory, the fundamental objects are strings at the string scale, which is expected to be close to but not identical to the Planck scale. In other approaches, space-time may be a causal set, a discrete, partially ordered set of events. Or it may be an emergent property of more fundamental quantum degrees of freedom, as the add-CFT correspondence suggests. Or it may have a non-commutative geometry, in which the coordinates of space-time satisfy an uncertainty relation similar to the position-momentum uncertainty relation. Each of these proposals is motivated by specific theoretical considerations and makes specific predictions that in principle could be tested. The challenge is that direct tests at the Planck scale are not currently feasible with any technology we can envision. The indirect tests, looking for small deviations from standard predictions in astrophysical observations, quantum optics experiments, and precision atomic physics, are at the frontier of current experimental capability. Ready to change how you see the world? The question of what space-time is at its deepest level, the question that the incompatibility of quantum mechanics and general relativity forces on us, is one of the most profound, open questions in science. The 12 principles I have assembled for understanding the fabric of reality are organized around exactly the kind of thinking required to navigate these questions. Get your copy of 12 Principles for Understanding the Fabric of Reality at realityprinciples.com. Let me now describe the specific clues that the existing theories provide about what the final theory might look like, because each clue constrains the space of possibilities in a specific way. The first and most important clue is the holographic principle, which I described in the space-time video. Let me develop it here with the full physical content it deserves. The holographic principle emerged from the study of black hole thermodynamics, specifically from Bekenstein's discovery in 1972 that black holes have entropy proportional to their horizon area, and Hawking's discovery in 1974 that black holes emit thermal radiation. These two results together imply that a black hole with horizon area A has entropy S equals A divided by 4g in natural units where the Planck area is 1. The key insight is the comparison between the entropy of a system in a region of space and the maximum entropy that region can contain. For ordinary matter, the maximum entropy of a region scales with its volume. You can pack more information into a larger volume. For a black hole, the entropy scales with the surface area of the horizon, and the black hole has more entropy than any other configuration of matter with the same mass in the same volume. The black hole entropy is the maximum entropy that any configuration of matter with that mass can have in that volume. This means that the maximum information content of any region of space, including ordinary space with no black hole, is bounded by the area of the region's boundary divided by 4 times Newton's constant. This is Bekenstein's bound. You cannot fit more bits of information into a region of space than the region's area in Planck units divided by 4. The 3-dimensional region of space contains information bounded by a 2-dimensional quantity, its boundary area. This is the holographic principle. The degrees of freedom needed to describe a 3-dimensional region are encoded in the two-dimensional boundary. The maximum information content of a three-dimensional region scales with area, not volume, just as a hologram encodes a three-dimensional image on a two-dimensional surface. The holographic principle received its first precise mathematical formulation in the ADS CFT correspondence. The specific statement of the correspondence in its most studied form is type 2b string theory in the product spacetime of five-dimensional anti-de Sitter space with a five-sphere called ADS 5 times S5 is exactly equivalent to n equals 4 supersymmetric Yang-Mills theory, a four-dimensional conformal field theory on the four-dimensional boundary of ADS 5. Anti-de Sitter space is a spacetime with a negative cosmological constant. It has the geometry of a space that is constantly curving inward, like the interior of a hyperboloid. Its boundary is a lower dimensional surface, the conformal boundary on which the dual field theory lives. In the ADS CFT correspondence, the physics in the five-dimensional bulk, including gravity and all gravitational dynamics, is completely encoded in the four-dimensional boundary field theory, which has no gravity at all. The dictionary between bulk and boundary is precise and has been tested in many contexts. A bulk graviton corresponds to the stress-energy tensor of the boundary field theory. A bulk scalar field corresponds to a scalar operator in the boundary theory. The mass of the bulk field determines the scaling dimension of the dual operator through a specific formula involving the curvature scale of the anti-de Sitter space. The classical gravity limit of the bulk corresponds to the large n limit of the boundary theory, where n is the number of colors in the gauge group. Quantum gravity corrections in the bulk correspond to finite n corrections in the boundary theory. The Bekenstein-Hawking entropy formula in the bulk has a precise boundary interpretation. The entropy of a black hole in the bulk equals the entanglement entropy of a region in the boundary theory. This is the Ryu-Takayanagi formula, which extends the identification to any spatial region. The Ryu-Takayanagi formula states precisely, for a region A on the boundary, the entanglement entropy of the quantum state in region A equals the area of the minimal surface in the bulk whose boundary coincides with the boundary of region A divided by 4 times Newton's constant. Mathematically, SA equals the area of the minimal surface gamma A divided by 4G. The minimal surface gamma A is the geodesic surface in the bulk that ends on the boundary of region A and has minimal area. For a simple interval on the boundary in 2 dimensions, it is a geodesic arc in the bulk that looks like the shortest path connecting the two endpoints of the interval through the bulk anti-de Sitter space. The Ryu-Takayanagi formula has been confirmed in many calculations and is now understood as a consequence of the replica trick in the bulk gravitational path integral. It has been extended to quantum corrections, where the area term receives contributions from the bulk entropy of quantum fields, giving the quantum-corrected Ryu-Takayanagi formula, or equivalently the island formula that I will describe in the context of black hole information. The physical interpretation of the Ryu-Takayanagi formula is profound. The area of a surface in the bulk spacetime, which is a geometric quantity, equals the entanglement entropy in the boundary theory, which is a quantum information quantity. This is not just a coincidence or convenient equivalence. It means that the geometry of spacetime is encoded in quantum entanglement. The metric of the bulk spacetime, the object that general relativity uses to describe the geometry of space and time, is determined by the entanglement structure of the boundary quantum field theory. If you change the entanglement in the boundary theory, you change the geometry of the bulk. More entanglement between two boundary regions means more geometric connectivity between the corresponding bulk regions. The minimal surface between them has more area. Less entanglement means less connectivity. As I described in the spacetime video, if you completely disentangle two halves of the boundary theory, the corresponding bulk regions become geometrically disconnected, as if spacetime has torn apart. This is the origin of the ER equals EPR conjecture. Wormholes, which are geometric connections between two regions of space, are equivalent to quantum entanglement between the corresponding regions. The conjecture was proposed by Maldacena and Susskind in 2013 and has been developed extensively since. It provides the physical picture for why entanglement creates geometric connectivity. The minimal surface in the bulk, whose area gives the entanglement entropy, is the interior of the wormhole that connects the two entangled regions. The Bekenstein-Hawking entropy formula tells us that the information content of a region of spacetime scales with the area of its boundary, measured in Planck units rather than with its volume. This is the holographic principle. A three-dimensional region of space can be fully described by degrees of freedom living on its two-dimensional boundary. The holographic principle is not a speculation. It is a precise mathematical result of the AD-CFT correspondence. A specific theory of quantum gravity in three spatial dimensions is exactly equivalent to a specific non-gravitational quantum field theory on the two-dimensional boundary of that space. The reduction in dimensionality from bulk to boundary is exact and complete. If the holographic principle is a general feature of quantum gravity and not just a property of the specific AD-CFT setting, it has profound implications for the nature of space. The three spatial dimensions of our experience may not be fundamental. They may be an emergent description of a more fundamental theory that lives on a two-dimensional surface. Space itself, the three-dimensional arena in which all physical processes seem to occur, may be a projection of a lower dimensional reality. I use the word illusion carefully because it can be misleading. The three-dimensional space of our experience is real, in the sense that measurements performed within it give consistent, reproducible results that are described by the laws of physics. The holographic principle does not say that three-dimensional space is not real. It says that three-dimensional space is not fundamental. It can be fully described by a two-dimensional theory, which means that three-dimensional space is an emergent property of that theory, not a basic ingredient. This is a revolution in our conception of space, comparable to the revolution that relativity brought to our conception of time. Relativity showed that time is not the absolute external parameter of Newtonian physics, but a dimension of a four-dimensional spacetime that can be mixed with space by Lorentz transformations. The holographic principle suggests that the spatial dimensions themselves are not fundamental, but are emergent from a theory with fewer dimensions. The dimensionality of space is not a fixed fact about the universe, but a property of the low-energy, large-scale description. The second clue is the emergence of spacetime from entanglement. The Ryu-Takayanagi formula in ADS, CFT, which I described in the spacetime video, states that the area of the minimal surface in the bulk spacetime connecting two boundary regions equals the entanglement entropy of those regions in the boundary theory. More entanglement between boundary regions corresponds to more spatial connectivity in the bulk. Less entanglement corresponds to less connectivity. Remove all entanglement between two boundary regions and the corresponding bulk regions become disconnected, as if space is torn apart. This is the ER equals EPR conjecture in a precise form. The spatial connection between two regions of the bulk is equivalent to the quantum entanglement between the corresponding regions of the boundary. Space-time connectivity is entanglement. The geometry of space is the entanglement structure of the boundary quantum theory. If this is correct, then the fabric of space-time, the geometric arena that Einstein's general relativity describes as curved and dynamic, is woven from the threads of quantum entanglement. The curvature of space-time that we experience as gravity is a manifestation of the entanglement structure of the underlying quantum theory. Einstein's field equations, which describe how matter and energy curve space-time, must emerge from the dynamics of quantum entanglement in the boundary theory. This is being actively studied. The Einstein equations have been derived from the Ryu-Takayanagi formula and its quantum corrections in certain limits, a result that demonstrates in a specific and calculable setting that the laws of gravity emerge from entanglement. The research program of understanding exactly how and why this emergence occurs is one of the most active in fundamental physics. The third clue is the information paradox and its resolution. The black hole information paradox is one of the most important problems in theoretical physics, and its recent resolution via the island formula reveals something specific about the nature of space-time near the black hole horizon that the final theory must explain. Hawking's 1974 calculation of black hole radiation used quantum field theory in a fixed curved space-time background. He treated the space-time geometry of the black hole as a fixed classical background and computed the quantum mechanical emission of particles from the horizon region. The result was that the radiation is exactly thermal. It has the spectrum of a perfect black body at a specific temperature, and it carries no information about what fell into the black hole. If this were the complete story, the information would be destroyed as the black hole evaporated, violating the unitarity of quantum mechanics. Unitarity is a fundamental principle of quantum mechanics. The total probability of all outcomes of any physical process must equal 1. And this requirement implies that quantum evolution is reversible in principle. If you start with a specific quantum state, run it forward in time, and then run it backward, you recover the original state. Information is never destroyed. This is not a philosophical preference. It is a mathematical requirement of the Hilbert space formulation of quantum mechanics, and it is confirmed by every quantum mechanical experiment ever performed. The conflict between Hawking's thermal radiation and quantum mechanical unitarity is the information paradox. Either Hawking's calculation is wrong, or unitarity is wrong, or something more subtle is going on. For 4 decades, this question was unresolved. The resolution that has emerged over the past decade uses the quantum-corrected Ryu-Takayanagi formula. The key insight is that the entropy of the Hawking radiation, which determines whether the information is being preserved or destroyed, is not simply the thermal entropy that Hawking computed. It is the generalized entropy, which includes contributions from space-time regions called islands that are entangled with the exterior radiation. An island is a region of space-time inside or near the black hole horizon that makes a contribution to the entanglement entropy calculation, even though it appears to be causally disconnected from the exterior. The island contribution arises from a quantum-gravitational effect. In the full quantum gravity calculation, there are saddle points of the gravitational path integral that include topological connections between the interior and exterior of the black hole, specifically Euclidean wormhole configurations that connect the island to the exterior. These saddle points contribute to the entropy calculation even though they are exponentially suppressed in the classical limit. The result of including the island contributions is that the entropy of the Hawking radiation follows a specific curve called the Page curve. For the first half of the black hole's lifetime by entropy, the entropy of the radiation increases monotonically as Hawking's calculation predicted. This is consistent with both Hawking's calculation, which is valid early in the black hole's life when the island saddle points are suppressed, and with unitarity, because the entropy increase corresponds to the entanglement building up between the radiation and the black hole interior. At the Page time, the midpoint of the black hole's life by entropy, the island saddle points become comparable in importance to the original Hawking saddle point. The entropy starts to be dominated by the island contribution, which gives a decreasing entropy as the black hole shrinks. The information starts to be revealed in the correlations of the late-time Hawking radiation in a form that is enormously complex and essentially impossible to decode practically, but which is there in principle. After the page time, the entropy of the radiation decreases as the black hole shrinks, and the total entropy, radiation plus black hole, decreases as the black hole loses mass. This follows the page curve, which is the specific entropy evolution expected if the black hole is a unitary quantum system that preserves information. The island formula was derived rigorously in specific simple models of gravity coupled to matter in lower dimensions. Whether it applies to black holes in four-dimensional space-time with full quantum gravity is not yet proven, but is strongly suggested by the results. The island formula represents a significant breakthrough in the information paradox and provides the most complete resolution of the paradox currently available. What the island formula tells us about the final theory is specific. The geometry of space-time near and inside the black hole horizon cannot be fully described by classical general relativity. Quantum gravitational effects, specifically the island saddle points, are necessary to get the correct entropy evolution. The final theory must reproduce these quantum geometrical effects. It must describe the topological connections, the quantum wormholes that connect the island to the exterior, and it must do this in a way that is consistent with the unitarity of quantum mechanics. This is a specific and concrete requirement on the final theory that goes beyond the general incompatibility of quantum mechanics and general relativity. It requires a theory that can describe the quantum geometry of black hole interiors, including topological features like wormholes, in a way that is consistent with quantum information principles. No current theory of quantum gravity completely satisfies this requirement, though string theory and AD-CFT provide the most promising partial realization. The fourth clue is the swampland program. In string theory, the landscape of possible vacua contains an enormous number of four-dimensional universe configurations, estimated at 10 to the 500 or more. Most of these vacua have different low-energy physics, different particle spectra, different coupling constants, different cosmological constants. The question of which vacua, if any, are consistent with the constraints of quantum gravity has been studied intensively. The swampland program, developed by Kamran Vafa and collaborators over the past 2 decades, attempts to identify general constraints on effective field theories that arise from the requirements of quantum gravity consistency. The idea is that the space of all possible effective field theories, all possible theories of particles and forces, divides into 2 regions: the landscape, which consists of theories that can be consistently embedded in quantum gravity, and the swampland, which consists of theories that appear self-consistent in isolation but cannot be consistently embedded in quantum gravity. The swampland is much larger than the landscape. The swampland conjectures are proposed constraints that the landscape must satisfy and the swampland must violate. They are conjectures rather than theorems because they have not been rigorously proven from first principles, but they are supported by an enormous number of examples in string theory and other quantum gravity frameworks. The most important swampland conjecture for our understanding of the universe is the de Sitter conjecture, which states that any scalar field potential V in a consistent theory of quantum gravity must satisfy either dV, d phi divided by V is greater than or equal to a positive constant C, meaning the potential has a slope above a minimum value, or the second derivative minus d squared V divided by d phi squared is greater than or equal to another positive constant C prime. These conditions together forbid a stable de Sitter minimum, a point in field space where the potential is positive and has a flat minimum. De Sitter space is the space-time that a universe settles into if it has a positive cosmological constant and no other matter or energy. Our universe, currently dominated by dark energy that drives accelerating expansion, is asymptotically approaching de Sitter space as the matter and radiation dilute. If the de Sitter conjecture is correct, our universe cannot settle into a stable de Sitter state. Instead, the dark energy must be slowly rolling with the equation of state W, not exactly equal to -1. This is a testable prediction. Current observations from the Planck CMB satellite, the Baryon Oscillation Spectroscopic Survey, and supernovae measurements are consistent with a constant dark energy density, W equals -1, to the precision of current measurements, which is approximately 5%. The next generation of dark energy surveys, including the Dark Energy Spectroscopic Instrument, Euclid, and the Vera Rubin Observatory's LSST, will measure W to much better precision, potentially at the 1% level. If W differs from -1 by more than a few percent, the de Sitter conjecture is supported. If W is consistent with exactly -1 to high precision, the conjecture is under pressure. The distance conjecture is another important swampland constraint. It states that as you move a large distance in field space, in the space of possible values of scalar fields, an infinite tower of light states appears with masses that decrease exponentially with the field displacement. The distance is measured in units of the Planck mass. The intuition is that quantum gravity does not allow a single effective theory to be valid over arbitrarily large ranges of field values. As the field moves far from its vacuum value, new light degrees of freedom appear that invalidate the original effective field theory. The distance conjecture has been confirmed in a large number of string theory examples. It is related to the species scale, the energy scale at which quantum gravity effects become important, which decreases as more light states appear. The distance conjecture implies that in quantum gravity, you cannot take a fixed theory and simply vary a parameter to extreme values. The theory changes as the parameter varies, with new light states appearing. The distance conjecture has implications for inflation, the early period of accelerated expansion that is believed to have preceded the hot Big Bang. Inflationary models typically involve a scalar field, the inflaton, rolling down its potential energy by a large distance in field space. The distance conjecture constrains which inflationary models are consistent with quantum gravity, and in particular constrains the models with the largest field ranges, called large field inflation models. This provides a connection between the swampland program and the specific inflationary models that can be probed by CMB observations of primordial gravitational waves. The weak gravity conjecture is a third swampland constraint. It states that in any consistent theory of quantum gravity, any gauge force must satisfy a specific inequality between the charge to mass ratio of the lightest charged particle and the gravitational coupling. Specifically, the charge to mass ratio in Planck units must be greater than or equal to 1. This ensures that the electromagnetic force is at least as strong as gravity for the lightest charged particle, so that gravity is never the dominant force between fundamental particles. The weak gravity conjecture is satisfied in the Standard Model. The electron's charge to mass ratio in Planck units is approximately 8 times 10 to the 21, enormously larger than 1. But the conjecture has implications for extensions of the Standard Model, particularly for models with multiple U1 gauge symmetries or with very light particles. The swampland program as a whole provides a set of constraints on physics that are derivable from quantum gravity consistency, not from experimental data or theoretical prejudice about model building. These constraints narrow the space of possible theories of physics beyond the standard model and have implications for cosmology that are in principle observable. The program is actively developing, with new conjectures being proposed and tested, and it represents one of the most active areas of interaction between string theory and observational cosmology. What the swampland program illustrates is that quantum gravity, even though it operates at scales far beyond current experimental reach, leaves observable imprints on low-energy physics through the constraints it places on the effective theories that describe those low-energy phenomena. The final theory of quantum gravity is not just important for understanding the Planck scale. It constrains the entire landscape of physical possibilities at all scales, and some of those constraints are testable with current and near-future experiments. This is the fifth clue to the final secret. The swampland constraints reveal that quantum gravity is not isolated from the rest of physics. Its consistency requirements propagate down to low energies and leave specific imprints that we can search for in cosmological observations. The final theory of quantum gravity is connected to every aspect of physics, from the cosmological constant to the properties of elementary particles to the spectrum of inflationary perturbations. The five clues together: the holographic principle, an AD-CFT, the Ryu-Takayanagi formula, and the emergence of space-time from entanglement, the island formula for black hole information, the swampland program, and the de Sitter conjecture, and the direct observational constraints from astrophysics paint a specific and increasingly detailed portrait of what the final theory must look like. It must be holographic. It must reproduce space-time from entanglement. It must resolve the black hole information paradox through island contributions. It must satisfy the swampland constraints. It must reduce to general relativity and quantum mechanics in their respective domains of validity. And it must be consistent with the observational constraints from gamma ray bursts, gravitational waves, and black hole imaging. The space of theories consistent with all these requirements is narrowing. The final secret is not infinitely hidden. It is hiding in a specific place, leaving specific clues, and the accumulated evidence of a century of theoretical and observational physics is pointing toward it with increasing precision. What do you see the world look like through these principles? The way entanglement writes the geometry of space-time, the way the information paradox forces us to reconsider the geometry near black holes, the way the holographic principle suggests that space itself is emergent. The 12 principles in my book are about exactly this: the deep structural features of the universe that are revealed when you push the physics to its limits, ready to change how you see the world. Get 12 principles for understanding the fabric of reality at realityprinciples.com. Let me now describe the observational situation in more detail, because the experimental constraints on Planck-scale physics are more sophisticated than is typically appreciated, and some of them come from unexpected directions. The most powerful current constraints on Planck-scale physics come from astrophysical observations of high-energy photons and cosmic rays. In loop quantum gravity and some other approaches, the discrete structure of space-time at the Planck scale is expected to produce small corrections to the dispersion relation of photons, the relationship between a photon's energy and its velocity. In standard Lorentz invariant physics, all photons travel at exactly c regardless of energy. This is a fundamental symmetry of special relativity. Lorentz invariance. Some quantum gravity models predict that Lorentz invariance is violated at the Planck scale, with the velocity of a photon receiving a correction proportional to some power of the photon's energy divided by the Planck energy. The most commonly studied modification is a linear correction. The velocity of a photon of energy, E, is c times 1 plus or minus a coefficient of order 1 times E divided by the Planck energy. For an optical photon with energy of a few electron volts, this correction is approximately 10 to the minus 28, utterly undetectable in any laboratory. But over cosmological distances, the accumulated time delay can be significant. A photon with energy E traveling a distance d accumulates a time delay relative to a zero-energy photon of approximately d times E divided by c squared times the Planck energy. For d equal to a cosmological distance of a few gigaparsecs, 1 gigaparsec is approximately 3.26 billion light-years, and E equal to 1 GeV, the time delay is approximately 10 to the minus 3 seconds. This is small, but potentially detectable if the emission time of the photon is known, and other explanations for the delay can be ruled out. Gamma ray bursts are the natural sources for this test. They are the most energetic explosive events in the universe, emitting photons at energies from kilo-electron volts to tens of GeV at distances up to and beyond 10 gigaparsecs. Most importantly, the gamma ray burst emission is expected to occur over a very short time at the source, from milliseconds to a few seconds, which makes the source time delay small compared to any propagation delay. If different energy photons from the same gamma ray burst arrive at Earth at different times, the time difference can be attributed to Lorentz invariance violation. The Fermi Gamma Ray Space Telescope, launched in 2008, has detected gamma ray bursts at energies up to tens of GeV. The most constraining result is from GRB 090510, a short gamma ray burst at a redshift of approximately 0.9 detected by Fermi's Large Area Telescope in 2009. The burst emitted photons at energies up to 31 GeV, and the highest energy photon arrived approximately 0.8 seconds after the start of the burst, which is consistent with the burst's intrinsic emission properties. The analysis placed a constraint on the Lorentz invariance violation scale of greater than 1.2 times the Planck energy for linear corrections. This constraint, greater than the Planck energy, is significant. It rules out the simplest and most natural linear Planck-scale correction to the dispersion relation. Whatever the final theory of quantum gravity is, if it violates Lorentz invariance at the Planck scale with a linear energy dependence, the Fermi constraint rules it out. The constraint does not rule out quadratic Planck scale corrections, which are suppressed by E squared divided by the Planck energy squared and are too small to be detected in current astrophysical observations. But it places the strongest constraints on the linear class of models. The gravitational wave speed measurement is another high precision constraint. In general relativity, gravitational waves travel at exactly c. Some modified gravity theories predict that gravitational waves travel at a different speed, which would produce a time delay or advance relative to electromagnetic signals from the same source. On the 17th of August 2017, the LIGO and Virgo detectors simultaneously detected the gravitational wave signal from a binary neutron star merger designated GW170817. Approximately 1.74 seconds later, the Fermi Gamma Ray Burst Monitor detected the associated Gamma Ray Burst GRB 170817A from the same source. The source was subsequently identified at a distance of approximately 40 megaparsecs, or about 130 million light years. The 1.74 second delay is consistent with astrophysical processes at the source. The gamma ray burst is expected to be emitted after the merger, not simultaneously. Accounting for a plausible range of source delays, the constraint on the difference between the gravitational wave speed and the speed of light is the absolute value of the quantity v GW minus c divided by c is less than approximately 10 to the minus 15. This is an extraordinary constraint. Gravitational waves travel at the speed of light to within 1 part in 10 to the 15. This rules out a wide class of modified gravity theories and constrains the dispersion of gravitational waves at the millihertz to kilohertz frequencies probed by LIGO. It is consistent with general relativity and inconsistent with any theory that predicts a significant difference between gravitational and electromagnetic wave speeds. The Event Horizon Telescope provides the most visually compelling evidence for general relativity in the strong field regime. The images of the black hole shadows in M87 and Sagittarius A, released in 2019 and 2022 respectively, show a dark central region surrounded by a bright ring, exactly as general relativity predicts for photons orbiting just outside the photon sphere of a Kerr black hole. The photon ring corresponds to photons in unstable circular orbits near the black hole at approximately 1.5 Schwarzschild radii. The size of the ring is proportional to the black hole mass and inversely proportional to the distance to the Earth, providing a direct measurement of the black hole mass if the distance is known. For M87, the measured mass is approximately 6.5 billion solar masses. For Sagittarius A, the measured mass is approximately 4 million solar masses. Both measurements are consistent with independent mass estimates from stellar dynamics, confirming the prediction of general relativity. The shape of the photon ring, in particular the existence of a photon sphere and the specific lensing pattern of the accretion disk emission, is a test of the Kerr metric, the space-time geometry of a rotating black hole in general relativity. Deviations from the Kerr metric, which could arise from quantum gravity corrections or from exotic matter near the black hole, would change the ring shape in specific ways. The Event Horizon Telescope observations are consistent with the Kerr metric with no statistically significant deviations. Future observations with the Event Horizon Telescope and its planned extensions, including space-based baselines that would increase the angular resolution, will probe the photon ring structure with higher precision. Subtle deviations from the Kerr photon ring, if present, would indicate physics beyond general relativity in the strong field regime. The combined evidence from Fermi gamma ray burst observations, gravitational wave speed measurements, and Event Horizon Telescope imaging establishes that general relativity is consistent with all current observations in both the weak field and strong field regimes, and that any departures from general relativity at the energies and scales currently accessible are smaller than the measurement precision. The final theory of quantum gravity must reduce to general relativity in these regimes to the precision of current observations. Let me now describe what I believe are the most important conceptual shifts that the discovery of quantum gravity will require, because understanding what must change is as important as understanding what is currently known. The first shift is the emergence of spacetime. I have described this in the context of AD-CFT, where the bulk spacetime geometry emerges from the entanglement structure of the boundary quantum field theory. The most important implication of this emergence is that space and time are not fundamental ingredients of the final theory. They are approximate, large-scale descriptions that arise from the dynamics of more fundamental degrees of freedom that do not themselves live in space or time. This is conceptually radical in a way that is difficult to fully appreciate from within the framework of space-time-based physics. Everything we know is described in the language of space-time. Our experiments occur at specific locations at specific times. Our measurements produce numbers that are defined relative to a space-time framework. Even the language in which physics is described, the differential equations, the Hilbert spaces, the action principles, are all formulated in terms of space-time coordinates. To say that space-time is not fundamental is to say that the framework in which all of our experience and all of our measurements occur is not the most basic description of reality. The analogy that I find most useful is the emergence of temperature from molecular motion. Temperature is a real and measurable property of a gas. You can put a thermometer in a gas and measure its temperature with arbitrary precision. Temperature obeys specific laws, the laws of thermodynamics, including the 0th law that defines thermodynamic equilibrium, the first law that defines internal energy, the second law that defines entropy, and the third law that defines absolute zero. So these laws are exact and universally applicable within their domain. But temperature is not a fundamental ingredient of the gas. It is an emergent property of the average kinetic energy of the molecules. At the molecular level, there is no temperature, only the positions and velocities of individual molecules and the forces between them. Temperature is a statistical concept that emerges when you describe many molecules collectively rather than individually. If you could track every molecule individually, you would not use the concept of temperature at all. In the same way, space-time is a real and measurable property of the universe. You can measure distances and time intervals, and they obey specific laws, the laws of general relativity. But if the holographic principle is correct, space-time is not a fundamental ingredient of the universe. It is an emergent property of the entanglement structure of more fundamental degrees of freedom that do not themselves live in space-time. At the level of those degrees of freedom, there may be no space-time, only the abstract quantum state and its information structure. Space-time emerges from the statistical and quantum mechanical properties of many fundamental degrees of freedom, just as temperature emerges from the statistical properties of many molecules. This emergence is not approximate in the way that fluid dynamics is an approximate description of molecular dynamics. It is exact in the AD-CFT correspondence. The bulk space-time physics is exactly equivalent to the boundary field theory physics. The emergence is a precise mathematical duality, not an approximation. The bulk gravitational theory is a faithful description of the same physical system as the boundary non-gravitational theory, not an approximation to it. The second shift is the dissolution of the boundary between quantum and gravitational physics. The incompatibility of quantum mechanics and general relativity that I described at the opening is not just a technical problem, it is a conceptual problem. The two theories use fundamentally different concepts of reality. In the final theory, there will not be a quantum realm and a classical realm. There will be a single, coherent description in which quantum and gravitational effects are unified from the start. The classical world of general relativity and the quantum world of the Standard Model are both approximate descriptions that emerge from the final theory in their respective domains of validity. The third shift is the reconception of the Big Bang. The classical Big Bang singularity, the point at t equals 0 where the classical theory breaks down, will be replaced by something quantum. The final theory of quantum gravity will give a specific and precise answer for what happened at the Planck epoch, the first 10 to the minus 43 seconds, when the energy density was at the Planck scale. This answer will determine the initial conditions of the universe in a way that is not arbitrary. The specific initial entropy of the universe, which is extraordinarily low compared to the maximum possible entropy, must be explained by the fundamental theory, not assumed as a boundary condition. The fourth shift is the understanding of time. The problem of time and quantum gravity, which I described in the space-time video, is one of the deepest obstacles to constructing a quantum theory of gravity. In the final theory, time will emerge from the dynamics in a way that has not yet been understood. The direction of time, the arrow from past to future, will be explained by the fundamental theory rather than assumed as a background structure. The specific mechanism by which time emerges may be connected to the entanglement structure of the vacuum state. Several proposals suggest that the flow of time, the thermodynamic arrow, and the expansion of the universe are all connected to the entanglement structure of the quantum fields and the quantum gravity degrees of freedom. Whether this connection is deep and necessary or accidental and contingent is not yet known. These four conceptual shifts, the emergence of spacetime, the dissolution of the quantum-gravitational boundary, the reconception of the Big Bang, and the understanding of time, are what the final theory must achieve. They are the content of the final secret, not a specific equation or a specific particle or a specific experiment. A fundamental reconception of what space, time, matter, and existence are at the deepest level accessible to physics. The universe is hiding this secret at the Planck scale, 14 orders of magnitude below what we can currently probe. The clues are real and accumulating. The holographic principle, the Ryu-Takayanagi formula, and the emergence of space-time from entanglement, the island formula for black hole information, and what it implies about quantum geometry, the swampland constraints and the de Sitter conjecture, the gamma-ray burst photon timing limits, the gravitational wave speed measurement, the event horizon telescope images. Each clue narrows the space of possible final theories. Each experiment that confirms the predictions of general relativity and quantum mechanics in their respective domains of validity is also a constraint on what the final theory must reduce to in those domains. The discovery of quantum gravity, when it comes, will be the most fundamental advance in physics since quantum mechanics itself. It will change our understanding of space and time, of the Big Bang and the ultimate fate of the universe, of the nature of information and entropy, and of the relationship between the mathematical structures we use to describe reality and reality itself. It will likely require a conceptual leap comparable to the leap from Newtonian mechanics to quantum mechanics, or from Newtonian gravity to general relativity. The physicists working on this problem know this. The research programs of string theory, loop quantum gravity, causal dynamical triangulations, causal set theory, and the many other approaches to quantum gravity are unified by the recognition that something fundamentally new is required. The disagreements are about what that new thing is, not about whether it is needed. The universe is hiding one final secret. The secret is the nature of space-time at the Planck scale. The discovery of that secret will be the culmination of the scientific project that began with Newton and was transformed by Einstein and Bohr and Heisenberg and Dirac. It is the last question at the foundations of physics. And the answer is out there, hidden in the geometry of space at distances of 10 to the minus 35 meters, waiting for the framework that can see it clearly. What I find most remarkable about this situation, and what I think deserves more appreciation in popular discussions of physics, is that we are not simply ignorant. We know what we do not know. We know precisely where the breakdown occurs. We know which clues are pointing toward the answer. We have a clear and specific target, a quantum theory that is background independent, that reduces to general relativity in the classical limit, and to quantum field theory in the flat space-time limit, that resolves the black hole information paradox through the island formula, that is consistent with the holographic principle and the Ryu-Takayanagi formula, and that survives the swampland constraints. This is an extraordinarily well-specified target for a future theory, and the fact that we can specify it so precisely is itself one of the major achievements of theoretical physics in the late 20th and early 21st centuries. In the history of physics, there have been very few moments when the specific form of the next revolution was visible before it arrived. The ultraviolet catastrophe of classical statistical mechanics pointed specifically to energy quantization. The null result of the Michelson-Morley experiment pointed specifically to the relativity of simultaneity. The incompatibility of quantum mechanics and general relativity points specifically to the emergence of space-time from quantum entanglement. The final secret may already be visible in the equations we have. The theory of everything may be something we can already see the outline of, even if the full picture is not yet in focus. What do you see the world look like through these principles? The way entanglement writes the geometry of space-time, The way the information paradox forces us to reconsider the geometry near black holes. The way the holographic principle suggests that space itself is emergent. The 12 principles in my book are about exactly this, the deep structural features of the universe that are revealed when you push the physics to its limits. Ready to change how you see the world? Get 12 principles for understanding the fabric of reality at realityprinciples.com. Let me now describe the two most active research programs toward quantum gravity, string theory and loop quantum gravity, in more depth, because understanding what each achieves and where each falls short illuminates why the final theory has not yet been found. String theory, as I described in the spacetime video, is built on the premise that the fundamental objects are not point particles, but one-dimensional strings. In 10 dimensions with supersymmetry, the theory is anomaly-free, and the massless spin 2 excitation of the closed string is the graviton, providing a UV-complete theory of quantum gravity. The ADS CFT correspondence, one of the most powerful results in theoretical physics of the past 30 years, was discovered within string theory. The island formula and the swampland program are both products of string theory research. String theory provides the most developed and most internally consistent approach to quantum gravity currently available. The specific successes of string theory in quantum gravity include providing a microscopic explanation for the Bekenstein-Hawking entropy of certain extremal black holes through the Strominger-Vafa calculation, which counted the number of d-brane microstates and showed it matches the entropy formula, providing the AD-CFT correspondence, which gives a non-perturbative definition of quantum gravity in certain spacetimes through the boundary field theory, and providing the swampland program, which identifies constraints on effective theories from quantum gravity consistency with specific predictions for cosmology. The limitations of string theory include the requirement for supersymmetry, which has not been observed at LHC energies, the enormous landscape of vacua, which makes specific predictions difficult without an additional selection principle, and the challenge of constructing stable de Sitter vacua, which has been the subject of significant controversy and connects to the swampland de Sitter conjecture. Loop quantum gravity takes a completely different approach, where string theory introduces new degrees of freedom, the strings and the extra dimensions, to achieve a consistent quantum gravity. Loop quantum gravity attempts to quantize gravity directly using only the degrees of freedom of general relativity. The key innovation of loop quantum gravity is the use of Ashtakar's reformulation of general relativity. Instead of describing gravity in terms of the metric tensor, Ashtakar showed in 1986 that general relativity can be reformulated in terms of connection variables, specifically an SU2 gauge connection that have the same mathematical structure as the Yang-Mills gauge theories of the Standard Model. This reformulation makes the quantization of gravity more tractable, because the same mathematical tools used for non-abelian gauge theories can be applied. The physical Hilbert space of loop quantum gravity is spanned by spin network states. A spin network is a graph whose edges are labeled by half-integer spin quantum numbers and whose nodes are labeled by invariant tensors of the SU2 gauge group. The spin network represents the quantum state of the three-dimensional spatial geometry. Each edge carries a quantum of area proportional to the square root of j times j plus 1 times the Planck area, where j is the spin label of the edge. Each node carries a quantum of volume determined by the spins of the incident edges. The area and volume operators in loop quantum gravity have discrete spectra. Area and volume come in discrete quanta with minimum non-zero values at the Planck scale. This is the most distinctive prediction of loop quantum gravity. Spatial geometry is quantized with a discrete structure at the Planck scale that replaces the smooth continuum of classical general relativity. The dynamics of loop quantum gravity is described by the Wheeler-DeWitt equation, or by the spin foam formalism, which provides a covariant version of the theory. In the spin foam formalism, the amplitude for a transition between two spin network states is given by a sum over spin foams, which are two-dimensional cell complexes that interpolate between the initial and final spin network states. The spin foam amplitude is a quantum analog of the Regge calculus discretization of general relativity. Loop quantum cosmology, which applies the methods of loop quantum gravity to homogeneous isotropic cosmologies, makes specific predictions that distinguish it from classical cosmology. The most important is the replacement of the Big Bang singularity by a quantum bounce. When the energy density reaches the Planck density, the quantum geometry correction reverses the collapse and the universe bounces to an expanding phase. This is the basis for the cyclic universe models I described in the Big Bang bounce video. Loop quantum gravity also predicts corrections to the graviton dispersion relation at the Planck scale, which could in principle be detected through gamma-ray burst photon timing observations. The specific form of the correction depends on the details of the spin foam model, and the current observational constraints from Fermi have ruled out some but not all of the proposed corrections. The limitations of loop quantum gravity include the difficulty of recovering smooth spacetime from the discrete spin network states in the macroscopic limit, which requires showing that the spin network dynamics reproduces general relativity at long wavelengths, the difficulty of incorporating matter fields and ensuring they couple correctly to the quantum geometry, and the challenge of connecting the theory to the holographic principle and adds CFT, which are better understood in the string theory framework. A third approach that deserves mention is causal set theory. Causal set theory was developed by Raphael Sorkin and collaborators beginning in the 1980s, motivated by the insight that the causal structure of space-time, the partial ordering of events by whether one can causally influence the other, is the most fundamental geometric structure that any quantum theory of space-time must preserve. In causal set theory, the fundamental entities are not points in a continuum, but a discrete set of events with a partial order structure that encodes causal relationships. The causal set is a finite set C together with a partial order relation that is transitive. If A precedes B and B precedes C, then A precedes C, irreflexive, no event precedes itself, and acyclic. If A precedes B, then B does not precede A. The manifold of classical general relativity emerges as an approximation to the causal set when the causal set is sufficiently large. The specific prediction of causal set theory that has received the most attention is the discreteness of space-time at the Planck scale. The number of space-time events in any region of four-dimensional space-time is approximately equal to the volume of that region in Planck units. This means that space-time, like matter, comes in discrete units, and the Planck volume is the minimum volume of any space-time event. Causal set theory has made a specific and unexpected prediction for cosmology, the value of the cosmological constant. Sorkin's prediction, made before the discovery of the accelerating expansion of the universe in 1998, was that the cosmological constant should have a value of order 1 divided by the Hubble volume in Planck units, which gives a value consistent with the observed dark energy density. This prediction was a significant early success for causal set theory, though its derivation involves assumptions about the quantum dynamics of causal sets that are not yet fully understood. These three approaches, string theory, loop quantum gravity, and causal set theory, represent different fundamental choices about what is primary in quantum gravity. The strings and extra dimensions of string theory, the quantized geometry of loop quantum gravity, or the causal structure of causal set theory. Each approach has achieved significant results and faces significant challenges. The final theory may be one of these, or it may be something different that incorporates insights from all three. What all three approaches agree on is that something genuinely new is required, a framework that is not simply quantum mechanics plus general relativity, but something qualitatively different from which both emerge as limits. And all three approaches agree that the new framework will have distinctive predictions for phenomena at or near the Planck scale that are currently inaccessible to experiment, but may eventually be probed through the accumulation of indirect evidence. The 12 principles in my book are about exactly the kind of thinking required to hold all of this simultaneously. The confirmed knowledge, the specific clues, the well-defined open questions, and the disciplined uncertainty about what lies beyond current knowledge. Ready to change how you see the world? Get 12 principles for understanding the fabric of reality at realityprinciples.com. What approach to quantum gravity do you find most compelling and why? Tell me in the comments. Let me close by situating this final secret in the history of physics, because I think the historical perspective reveals something important about where we are and what is likely to come. The history of fundamental physics is a history of conceptual revolutions, each of which did two things simultaneously. It explained something that had been mysterious, and it revealed that the explanation required a fundamentally new concept that had not existed before. Newton's mechanics and gravitational theory explained the planetary orbits, the fall of objects, and the tides. But the key concept it required, absolute space and absolute time as fixed backgrounds, seemed obvious in retrospect. Of course, there is a fixed space in which things move, yet it was a new concept, replacing the Aristotelian framework of natural places and natural motions. The concept of absolute space was so fundamental to Newton's mechanics that challenging it seemed impossible for 2 centuries. Maxwell's electromagnetic theory explained light, radio waves, and the relationship between electricity and magnetism. The key concept it required, the electromagnetic field as a physical entity that exists even in the absence of charges, was new. The field is not just a mathematical tool for calculating forces. It is a real physical thing that carries energy and momentum. This concept was so unfamiliar that physicists initially insisted on filling space with an aether to give the field something to wave in. Special relativity explained the null result of the Michelson-Morley experiment and the invariance of Maxwell's equations. The key concept it required, the unification of space and time into a 4-dimensional spacetime with a specific geometry, was radically new. Time is not absolute. Simultaneity is not universal. The speed of light is the same for all observers, not because of some mechanical property of the ether, but because of the geometric structure of spacetime. This concept required abandoning the most basic intuitive assumptions about how space and time work. Quantum mechanics explained the spectrum of hydrogen, the photoelectric effect, and the stability of atoms. The key concept it required, the wave function and quantum superposition, was radically new. Physical reality at the quantum level is not a definite state that exists independently of observation, but a superposition of possible states that collapses to a definite outcome upon measurement. This concept required abandoning the classical assumption that physical quantities have definite values independent of measurement. General relativity explained the perihelion precession of Mercury, the bending of starlight by the sun, and the expansion of the universe. The key concept it required, that gravity is the curvature of space-time caused by energy and momentum, was radically new. Gravity is not a force that acts at a distance, but a geometric property of space-time. Objects fall not because they are attracted, but because they follow geodesics in a curved geometry. This concept required abandoning the Newtonian picture of gravity as a force. In each of these revolutions, the new concept was not simply a refinement or extension of the previous framework, it was a reconception. Absolute space became the curved spacetime of general relativity. Definite trajectories became probability amplitudes in quantum mechanics. Gravity as a force became gravity as geometry. The incompatibility of quantum mechanics and general relativity is pointing toward another reconception of the same depth. The fixed classical background of quantum mechanics and the dynamical geometry of general relativity cannot both be fundamental. Something must give. The holographic principle, the Ryu-Takayanagi formula, and the ER equals EPR conjecture are all pointing toward the same reconception. Space-time is not fundamental. It emerges from something more basic, which appears to be quantum entanglement. The key concept of the next revolution may already have a name: entanglement geometry. The idea that the geometry of space-time, including the dimensionality of space, the curvature of space-time, and the connectivity of distant regions, is encoded in and determined by the quantum entanglement structure of the underlying degrees of freedom. This is not just a vague idea. It has been made mathematically precise in specific settings through the AD-CFT correspondence. It makes specific predictions that have been confirmed in many calculations. It provides a resolution of the black hole information paradox through the island formula. Whether entanglement geometry is the key concept of the final theory, or whether that concept has not yet been invented, is not yet known. But the pattern of history suggests that the concept will be as radical and as unexpected as quantum superposition was to the physicists of 1900 and as the curvature of space-time was to the physicists of 1910. The universe's final secret will be revealed by a conceptual revolution, not just by a more precise calculation. The specific evidence we have, the holographic principle, the Ryu-Takayanagi formula, the island formula, the ER equals EPR conjecture, the swampland constraints, all point toward the same reconception. The universe is built on quantum information. Space-time is the geometry of entanglement. The curvature of space-time that Einstein described and that we have measured in gravitational wave detectors and in the images from the Event Horizon Telescope is the macroscopic low-energy description of an entanglement structure in the underlying quantum degrees of freedom. The final secret of the universe is not that space-time is curved. Einstein told us that a century ago. The final secret is what space-time is made of at the most fundamental level, and the answer that the current evidence is pointing toward is quantum entanglement. The geometry of the universe is the pattern of quantum correlations between its most fundamental constituents. The universe, at its deepest level, is woven from entanglement. Whether this specific interpretation is correct, or whether the final theory will surprise us with something even more unexpected, is what remains to be discovered. The physicists working at the frontier of quantum gravity are searching for exactly this answer, using the clues I have described, pursuing insights from string theory and loop quantum gravity and causal set theory and many other approaches, constrained by the observational results from Fermi and LIGO and the Event Horizon Telescope. The final secret is known to be there. It is known to be at the Planck-scale. It is known to involve the relationship between quantum mechanics and space-time geometry. And the clues to its specific form are accumulating. The most important discovery in the history of science is waiting to be made. I do not know when it will come, or from which direction, or which currently obscure idea will turn out to be the key insight, but the history of physics suggests it will come from someone who takes the existing clues seriously, follows them wherever they lead without flinching from the radicalism of the conclusion, and proposes a new concept that is genuinely new rather than a refinement of existing frameworks. That is the nature of the final secret. That is what the universe is hiding, and the search for it is the most important thing happening in fundamental physics right now. If this changed how you think about the incompatibility of quantum mechanics and general relativity and what it means for the future of physics, if the holographic principle, the ER equals EPR conjecture, and the island formula look different now as specific clues to the final theory rather than isolated results, tell me in the comments. Tell me whether you find string theory or loop quantum gravity more compelling as a framework for quantum gravity, and why. Tell me whether the idea that space-time itself is emergent from entanglement changes how you experience the physical world you move through. And subscribe if you want to keep going into the places where the most fundamental questions in physics are still open, where the universe is still keeping its final secret, and where the answer is the most important discovery that science has left to make.